So we're sitting in my office here at ASU. Tom, who is a former student here, is now at UC Berkeley, but continued to collaborate with us on some of the silk stuff he did here as a student. And he's now doing some great work in Reimer's lab, along collaboratively with Omar Yagi and Austin Angel and others on some exciting MOF stuff that I'll have to tell you another time. And Chinchin's here from the group as well, who's at MRS this week. And we have a lot of people in from MRS this week, and it's nice that they're stopping by ASU. Tom, we actually just finished, and I want to say, I dare say, just accepted into Langmuir our second paper on Embiids silk. The first one was done along with Bennett, Addison, and others a few years ago, and unfortunately Jacob's not here as well. And Tom's going to tell us, though, this is kind of a practice to the MRS talk you're giving. What?
Yeah, it's tomorrow. It's 2.
It's at 2. When's your talk tomorrow?
Yeah. It's at 2:50.
Oh,
okay,
so you're both giving your
I'm
talk.
going to jump out real quick, I guess, and go over to yours.
So everyone who listens to his talk, he has a legitimate excuse of why he didn't stay till the end of the session. Thanks.
All right, so let's get started. So basically what I'm going to be doing in this talk is talking about, I guess, just the past 2 papers we've done, and that sort of covers the structural and physical properties of what is actually a nanofiber silk, nanomaterial sort of thing. It's a natural material, though. All right. So silk is just an incredible material in general. It's a protein-based fiber that has a high strength-to-weight ratio, and it's very extensible. It's known for being, elastic and very strong, but it's also biocompatible, so it's seeing a lot of new medical applications. And most people know silk from spiders and Embiids, and so they're often called web spinners, but I think that's kind of a vague term. It makes it seem like they're spiders or something like that. So I usually just use the word Embiid, also called Embiopterans. And they're a tropical or subtropical species. They live in groups. They're not as organized as ants and bees, and they don't have like a hierarchical structure, but they do kind of group together in these colonies where they spin silk tunnels. So the silk has this interesting property where it grips where water will grip to the surface, and what Embiids will do is then bite a hole in their silk sheet and drink it from within their gallery. So they're able to never have to leave the comfort of their home and still get access to it.
Remember, that video is on...
it's a BBC video.
It's a BBC series by
David Attenborough.
David Attenborough, and he did a whole thing on silks where he did from spiders but he worked with Janice, with our collaborator. It was Janice who did that. So Janice Edgerly wrote at Santa Clara was the one who provided the Embiids and everything for him to come and shoot.
So when they do those shots inside of the they do the shots inside the galleries.
If you haven't seen that BBC series, I can't remember the title, but it was something like Uncovering.
It's like Life Beneath Silk Tents or something. I don't know, something like
that. It was a really good
silk. They have these forelimbs on the ends of their, they're very swollen, and they have these they're called tarsi is what they're called. And what you see here is a scanning electron microscopy image of one of these tarsi, and you see it's covered, the bottom surface is covered in these little hairs. And these hairs, actually, we go to a higher magnification, that is from whence the silk comes. You can see in this image at high magnification, and based on the scale bar, that's a really thin fiber of silk. So it's actually on the nanoscale is what this silk is. And if we go to the next slide, just for some comparison, this is a human hair, so it's on the order of 50 to 100 microns. That's actually my hair, if you're interested.
Do you have dandruff?
No, that's just what all hair looks like.
That's what all hair
looks like.
Was this when you had long hair?
No. So at the same magnification, this is a spider silk right here. It's only microns thick, so already spider silk is much thinner than a human hair. But if we go even at the same magnification, but to Embiid silk, you can see right away that this is just a bundle that's on the order of microns, but there's lots of little tiny fibers. And we go into higher magnification, and you can see that these fibers are actually 90 to 100 nanometers in width. So this is really a nanoscale fiber, and it's actually the thinnest known arthropod silk that's been discovered. And what we've also found is that these silk fibers are coated in a lipid layer. And so on the left is just sort of some natural silk, but if we treat it with an organic solvent mixture, in this case 2-to-1 chloroform methanol, and this is just a quick rinse, it's not very much of a wash at all, but we disrupt some sort of surface layer on there, and we see clumping and some sort of a roughening of the surface due to the lipids getting displaced from the fiber core. With a little bit higher resolution, we go to TEM, and we can see a transmission electron microscopy, and we can see contrast between some sort of outer layer and an internal fiber core, with the dark being this what we are calling the protein fiber core, and on the outside we assign that to be the lipid layer. And the reason we know that's probably a lipid layer is because we do the same treatment, but this time a little bit more complete, and we see that there's only the fiber.
Beautiful images to show in one quick picture what we've been working on for years now about looking at these outer layers of lipids.
Yeah, I mean, we had, this is one slide here, but we've had all sorts of indirect evidence that there's a lipid layer, and I mean, this SEM was about as good as we could get, because either you wash it completely away and it looks like nothing, or you do a light rinse and you're left with this clumpy thing.
And that looks like,
you're not even sure
that
what
looks
that
like
is.
hair with dandruff. Like
right,
that
you
looks
don't know what that is.
It looks
like
you gave it dandruff.
Yeah,
you gave
don't know what that
Embiids
is.
dandruff. But you're right. When Sherry came along, Sherry has no dandruff, clearly.
No, yeah, we can just see the contrast right away. I mean, even just that one image with the lipid, you don't even need to remove it. You can see that there's just some other outer layer there.
Yeah,
it's pretty cool.
Impressive.
It is. And we can just take that extract, actually. If we're washing it already with organic, we just take that organic and put it in a GCMS, and we see that we've got fatty acids, other lipids. It's a very complex mixture, and so we just know it's lipids, and that we're kind of happy with that.
Have we published the GCMS? I know it's really a collaboration with Pierre Herc's group.
Yeah, it was
Pierre that really made that possible.
All right, so yeah, we've got structural fibers of this. So we wanted to look not just at this lipid layer, but also the fiber protein. And we know from some cDNA studies of the repetitive sequence for the amino acids, and actually that the protein itself is this repetitive sequence, but then repeated many, many more times, and then ends in a unique terminal sequence. And so for all intents and purposes, we can really just think about this material, this silk material, as just being glycine, alanine, and serine, partitioned into different fractions. One a crystalline fraction. So we did some wide-angle X-ray diffraction, and you can see in this diffraction pattern, there's just like so much diffuse scattering. I mean, that comes from the amorphous component of the silk, but we do have some discrete reflections as well. And we're able to look from the broadening of these discrete reflections of the radial, that means going out from the center. We're able to use Shearer's formula and figure out that these crystallite domains are on average around 3 by 4 by 5 nanometers. And so that gives us a pretty good idea of how big those are, which is some good information. And if we look at the broadening about the ring, the azimuthal broadening, we can get an orientation factor for how these crystallite domains are oriented in the silk. And this orientation factor goes from 1 to negative 0.5, and it's dependent on an angle between the C-axis of the crystallite and the unit cell in the crystal domain. And the fiber axis. And what we find, actually, is that this orientation factor is 0.93, which means it's highly oriented with respect to the fiber axis. And we actually think that that's a lower bound, because if you look at the distribution of fibers, we did this on like a quote-unquote oriented fiber, but anytime you string just a single fiber of Embiid silk, you have a bundle of fibers.
Well, and what I would say here too is I want to say it's Warner Weber who.
Yeah, Warner did
all this. All this work was done at Argonne National Labs at BioCars, which is Sector 14, and Rob, we owe a lot to Rob Henning and the NIH grant that supports University of Chicago, and the NIH grant that supports this. Rob helped us build a fiber diffraction line that we originally used for spider silk, and now we can use for all these other silks. And Rob and Warner, and along with our collaborator there, Chris Benmore, really helped make a lot of this possible. And we have another longtime collaborator, senior scientist, Sujatha Sampath, that's helped us with this as well. I was just shocked. I expected this to be such a fine silk, and while it had all these I thought the unit cells might be huge, because there's hardly any break and stuff and they have about the same, unit
so that's not,
cells.
yeah, this is not the unit cell, that's the crystallite domain. The
but
unit
I mean,
cell
is much smaller, but you're right.
Right.
I misspoke there, but the crystallite size is not much different than you see in silkworm silk or spider silk. I mean, a little different dimensionality, but both in the kind of 2 to 5 to 10 nanometer range big. This is more square-like, while they're more kind of rectangular-like in spider silk, but still, you're getting the details. They're in just a very few nanometer range size, nanocrystallites, which is kind of surprising. I thought maybe this one might be bigger. And then, like you said, the orientation is amazing. I get that it's such a small fiber that it naturally.
I mean,
wants to
you're
orient.
probably going to orient on it just because there's not that much. So we can use solid state NMR actually too to get at some of this information as well. And so we did. So Bennett here did a really clever thing where we're using.
Bennett's now
he's at.
He's the NMR, one of the NMR managers at UC
He's at Davis. Yeah,
so he's going to be where Christy Koski is, our Breon person. Oh, that'll be fun.
Yeah, so we can use a 13C chemical shift of serine to kind of probe how much random coil versus crystalline component we have, and so we did the solid state NMR on the silk. Bennett he knew, since we knew the peptide sequence, we just made that peptide repeat in a peptide synthesizer and then treated it two ways. One where you just evaporate formic acid to put it into an all beta sheet conformation, and another way where you take that peptide and then put it into a lyophilizer to just get all random coil. And so then our solid state NMR of those peptides gives us pure beta sheet or pure random coil / helix. And what that does is we get the line width, the line shape, the chemical shift, and that informs our fit. So we can then go in and fit this Embiids silk spectrum, and we find that 70% of the serine residues are found in the crystalline environment, which agrees really well with our wide. From all these experiments, we can come up with a structural model for this silk fiber. We have a 90 to 100 nanometer thick fiber with a 5 to 10 nanometer thick coating of lipid on the outside. And in the fiber core, we've got mostly crystalline beta sheet domains that are on the 4 to 5 nanometer range in size, and they're highly oriented with respect to the fiber axis, and they're interspersed loosely between. This is such a unique silk. It's got such a high crystalline fraction, highly oriented crystalline domains. We figure it must have some interesting mechanical properties, but all of the mechanical testing in the literature has been, really weak. It says it's a weak silk, 150 megapascals, and that's nothing. That's not a very impressive sort of thing. But what made us kind of question it was previously no one had been really using SEM to study the fiber diameter, and anytime you do these mechanical testing studies, the fiber diameter is ultimately important. The tensile strength is force over cross-sectional area, and if your cross-sectional area is wrong because you didn't have the right fiber diameter, you're going to get a wrong tensile strength.
For spider silk, it's really hard. Yeah. Now these are like 90, 100 nanometers. So these are more or less impossible. But he gave us the idea of setting up these E cards where, they're with an E, like you stretch it across, in a sense, two openings. You can cut one of the openings so that you get the
so you can do mechanical testing on
the
that
mechanical testing, and then the other one you can do the SEM. This is just really pushing the limit, though. There's so many fibers, they're so thin. We think we have an idea, but it's really going to take a kind of a heroic experimental effort.
I'm thinking it would have to be used an AFM tip or something. I don't know what you would do, but these are such a small fiber.
But because of our error, we can easily have an error of plus or minus an order of magnitude here to where this stuff could potentially be
very strong. Well, and I wonder also just, this is just only the axial stress, right, on the fiber diameter. I'm interested in the full mechanical properties, like how tough is it on the, to put, if you had to hit it or something like that, how strong is it there? We get some of the other dimensions.
Perfect for some of that, and this is where, again, we'll plug our own stuff. Like, I worked with Christy Koski. Her and I have worked for years in developing Breon scattering techniques, which we were able to. It's probably one of the most cited things we've done in the last 10 years on spider silk, which is and most of the credit goes to the efforts of Christy for getting this experimentally done, because it's not trivial, but getting the full elastic tensor of silk. And this allows us to make real connections to some of the stuff Marcus Buehler and others done on real atomistic MD level calculations and others. To do that on this silk will be huge as well. To add AFM to look at, experimentally radial forces versus longitudinal forces will be really exciting in this stuff. It's right on the nanometer scale.
Basically, we were interested in the wetting properties of the silk as well. And so we did something where we studied the contact angle of water on the silk. And in general, contact angles are formed when you have an interface between a liquid and solid surface. And the angle we're talking about is at the three-phase contact line between air, water, and the surface. And so if you just have a mildly hydrophobic surface, imagine we just have a, just a lipid coating on a surface. You might expect something like you see in the left figure there. There's around a 90-degree contact angle, maybe a little higher. But if you're able to pattern it at the nanoscale to reduce the contact between the fraction of surface area that the liquid's actually touching, so that you're actually maximizing the air-liquid contact, you result in a higher macroscopic contact angle with the same sort of chemical surface. And so just by nanoscale patterning, you can do that. And nature takes advantage of this all the time. The next thing we'll show is, rose petals do this. They have the surface of a rose petal is covered in these microscale bumps with nanoscale ridges. And so you can see it has a very high macroscopic contact angle. But what's interesting also about the rose petal is that when you invert the surface that it's on, so do a 180-degree tilt angle, it stays in place. And so that's just a unique property of the physical dimensions of those microscale bumps. If you go to the next picture, this is like a cartoon picture of it.
You don't
Basically,
even know
the
this yet,
microscale bumps.
You guys, because I remember when you came to me and said, like, we need to do some contact angle, and I'm like, oh my god, I don't do contact angle stuff.
No, and I didn't either. I had to learn a lot to do this,
No, but it's amazing how much it really gets used. It's a simple thing. You can set it up at home. So what I did, my daughter, who's in 7th grade, so she just started, Riley, just started junior high, and she had to come up with a science fair project a while ago, and it's in the middle of when we're doing all this. And she has a bunch of ideas, and she actually had some ideas about plants and growing stuff and blah, blah, blah. But then she had another one about, like, surfaces, like, oh, if I, tilt the surface. And so I gave her, I said, I've seen some of these contact angles. I said, I wonder if there's anything, and sure enough on YouTube and stuff, like, you can, with your iPhone, set up, and I mean, it's obviously not, but they sell a freeware little app for contact
angle. Really? I had no idea. That's awesome.
Like, there's a freeware little app that it runs on ImageJ.
Oh, cool.
It's a little add-on to ImageJ, and as soon as you input something, it sits there and tries to find the contact angle and blah, blah, blah. And so you can literally, and you can buy these little macro lenses for your iPhone where where it basically just like attaches something right here. Right. And the hardest thing is just to get the lighting right.
Because you've got to get the contrast, otherwise your measurements mean nothing.
It's all the little details, and to make sure that you keep your phone in the plane of focus, because it's, those are all autofocus, they're not fixed focus things. But if you can get around some of the what I call trivial engineering things, you can do some very advanced research level measurements. At home, just on the side at home.
I mean, it's such a simple concept. You're putting you're just contacting two things, a surface and a liquid, and you get a lot of chemical information out of it. I mean, traditionally, the technique is always just done on a smooth surface, so you get an idea of the surface energy of it. But it's seeing a lot of new applications in these rough surfaces. Cryo SEM with Conrad, and we see that this is like a top-down view. So we're actually looking a little bit below. We wanted to do some a focused ion beam to cut away some of the droplets so we could get a better view of the interface, but we had a little trouble doing that. So basically we tilted the stage so you could see down below the surface, and what we see is the water droplet just sits on the first layer of fibers. It's not going below at all. So really only one layer is really all that's necessary. Who knows what's going on in the center of the droplet? Obviously I'm not trying to generalize completely, but we see from this very edge right here that it's really only sitting on that first layer of fibers. And so that's what's giving the high macroscopic contact angle. But if you look at what's happening in recession, so the next thing is a video. We just go right up. We have a video here of a receding droplet, and what you see going on there actually is you see the surface changes as you're moving. It's not a static surface. The surface moves as you're removing volume from the droplet. And what we see, if you run it one more time, you see these fibers bundle together and form these sites where they all bundle and pin the contact line together. So like right here and here. I'm trying to, I guess I can't really point with my finger.
That's what I'm here
That's
for.
what you're here for, yeah. So these sites here where fibers bundle together pinning the contact line. So originally the droplet is pinned perhaps due to the droplet in contact with maybe a few fibers that are spaced nanoscale apart, and so maybe it's trapped some air there, made a pinning site, or maybe it's a defect in the lipid coating that makes a hydrophilic contact, and it's pinned there for some reason. It's just it really likes to stay as a hydrophilic or maybe just an air-water contact, something. This is a video. We're still sort of going out of sequence, but the lipid coating really does matter. This is some silk that was treated with the organic solvent that we were mentioning before to remove the lipid layer, and it is not having that same sort of effect. In fact, the silk is now permeable, so the water will just go right through. And so we know right away that lipid coating is essential. Otherwise, you just don't have this effect. And really cool. And also the reason the lipid coating is essential, I don't have a figure or anything for this, but I can just speak to it. Conrad did a really cool and quick experiment where he coated the silk in Teflon. And so, you can see from SEM, it looks not macroscopically, but microscopically the same.
So he put just a thin layer there. I assume like a few atomic layers thick. Yeah, a few nanometers thick, so it didn't increase the diameter of the color.
Not by much, and it also and morphologically the surface looks the same, but it's just coated in Teflon, and it's still hydrophobic, obviously, because Teflon, low surface contact, high air-water interface, but it doesn't have the gripping effect anymore.
Really?
It lost the gripping
Which
effect.
reminds me, have we ever, because I assume we coat it with gold for the SEM.
Well, yes, we do the sputter coating just for visualizing,
Yeah, I wonder, it makes me wonder, if we coated it with gold and ran, it's gold.
Hydrophilic.
What it would do. I mean, it's just...
You could just do any surface coatings, really,
We could go to town there,
So this was just some of the conclusions, I guess, that we had. Overall, it's a really cool material. It's a very new material. A lot of people haven't even heard of this insect.
So really, we should just write cool.
Very cool.
Here. I mean, is there a reason to say anything else except cool material? Give us more funding. They haven't given us any funding for this yet.
No. But I think that this is a really, this material could inspire design of surfaces that can mimic this effect. Because up to this point, any surfaces mimicking the rose petal effect, yes, they can do the rose petal effect, but they don't grip water as tightly as this. And this is potentially way easier to make as a surface because electrospinning is already a method that people use to make these hydrophobic surfaces. And you can make, very, very thin diameter fibers with electrospinning. So it would be a cool way to approach this, I think.
And then we can thank everyone.
Thank everyone here.
Shin for holding this.
For holding.
Me for being an advance, a great advance.
Letting an undergrad do a lot of this research was pretty cool.
Janice for, otherwise we'd never even have this project. Greg, who had to leave us for San Diego, but God knows why you wouldn't want to. Yeah. Anytime you get a chance to go to San Diego, I think you got to take that, right?
Yep.
So who else?
Yeah, Sherry for TEM.
Oh, that's been amazing. Came in
so
kind of
cool.
Towards the end of this project and made huge difference. I think the
quality just went up.
Yeah, the paper we originally submitted compared to the one we're going to end up getting published, hopefully, is so much better because of both Conrad and Sherry on there.
Yeah.
So, Bennett left us a while ago for Davis, but got this started. So, and I think he went and visited Janice.
He did.
So, and Chin Chen, this wouldn't be possible without you here holding the screen because
I'm a diva.
We can't make Tom hold his own screen.
I can't hold